In this short video, we're going to use MOS to briefly explain how MOS transistor works, and also we're going to dive into one of the two MOS operations, use MOS as a switch, in the second slides. So let's get started. On the right side, this is the schematic symbol for the MOS transistors. It has 4 terminals: drain, source, gate, and body. So when you apply positive voltage between gate and the source, if that positive voltage is higher than the VT threshold of the MOS, a channel between drain and source is created. So now the transistor is conducting. Things are more obvious when you look at the cross-section of the MOS in the layout. So as we mentioned, right, as we just said, when you apply positive voltage between gate and source, when that voltage is higher than the VT threshold of the MOS, a lot of electrons is accumulated beneath the gate here in this channel here. So N plus region also had a lot of electrons. So drain and source are both N plus regions. So now plus the electrons you attracted beneath the channel here, the current now can be conducted through the channel. So how are we going to size the MOS transistors? We use W and L. L here in the layout, you can see actually it's a spacing between drain and source here. So that's essentially L, right? And the third point is, yeah, we just mentioned that when the VGS is more than VTH, the conducting channel shows up between drain and source right beneath the gate. So there are two operations, two typical operations for MOS transistors. One of those is use MOS transistor as a switch, right? Again, when you apply positive voltage on the gate, when that positive voltage, relative to the source and the drain is a lot higher, you can have a lot more electrons accumulated beneath in this area. So when we say that actually the channel is fully turned on, right? So when the channel is fully turned on, the MOS transistor gonna look like a switch. So when we say the MOS transistor is like a switch, how do we know that what kind of switch resistance we have? So of course you can go back to the Razavi book and check the equations over there. But the most important thing is you can remember that the MOS switch resistance is inversely proportional to WL ratio, which means the higher the WL ratio, the lower the MOS radius sum is, resistance here. Of course, if you drive the gate a little bit harder, right, VGS, when the VGS minus VTH of the MOS is a lot bigger, you're going to have the resistance a lot lower. The third one is the mobility. When you, actually this is a very important one. So as you may already know that the mobility of electrons is usually 2 to 3x of the mobility of holes, right? For the MOS, which we use example here, the MOS is use electron as the carrier to conduct the current, while PMOS use holes to conduct the current. So for the same size, for the same WL ratio, the same size MOS transistors, MOS rds sum is a lot lower than the rds sum of the PMOS, right? If you keep the size the same. So that leads to a very important point. So when you have a task to design a MOS switch, when a MOS switch rds sum need to be like, let's say, lower than 0.1 ohms or so, you find out that the MOS switch gonna take a lot of chip area. Chip area is equivalent to the cost to manufacture the chip. So the big the chip area the MOS transistor can take, it's gonna cost more to manufacture the MOS transistor. So you often see in the industry when a MOS switch RDS sum is lower than 0.0 ohms, most of the time, I'll say not 100% of the time, but most of the time you're gonna see that switch is made of MOS. Yeah, so just remember that. I mean, when you try to next time when you try to design MOS switch, remember when the RDS sum is lower, than 0.0 ohms, make sure you use MOS unless you have a very good reason not to use it. Thank you for watching. If you liked the video, please give us thumbs up. It means a lot to us.